Welcome to the 10th lecture of Control System 2. So last class we are discussing about the canonical realization of state space representation, and we have discussed about the controller canonical form, observer canonical form, observability canonical form, and controllability canonical form. Means if a transfer function is given, how we will get these standard forms. Today we are going to discuss about another two forms, that is diagonal canonical form and Jordan canonical form. So let us start to discuss with these two canonical realization. But before that, in the last lecture I did a small mistake while deriving the controller canonical form, which involves the derivative of inputs. Probably here, as I drawn a block diagram where I did a small mistake, that this GS YS by US, now we want to write in the form of like this, that there will be a block. Okay, the input will be US. I think that time I have written YS, and then we are taking a intermediate variable, suppose zeta of S, and then we have another block, and ultimately we will get Y of S. Now our intention will be to write this expression as Y of S by zeta of S into zeta of S by U of S, and that exactly we have done in this slide. So now we will move to discuss how to find out the diagonal canonical realization using transfer function. Okay, so here we start. So the transfer function is defined by equation number 33. We have taken a transfer function in nth order system we have taken, but the transfer function is little bit different from the earlier what we have discussed. Here we have expressed the denominator in the factored form, where we can identify the poles of the transfer function, that is p1 p2 pn, or minus p1 minus p2 minus pn are indicating the poles of the transfer function. So here we can see, or we have to, once a transfer function is given and if it has been asked to find out the diagonal canonical form, our work will be to factorize the denominator and to express it in the form of s plus p1, s plus p2, s plus pn, such that we can identify what are the poles of the transfer function. And once it is written in the form of 33, then using partial fraction expansion we can write immediately b0 plus c1 by s plus p1 plus c2 by s plus p2 plus cn by s plus pn, where cn, c1, c2, cn are constant. And here one important thing you have to remember, the transfer function we are dealing where the poles are distinct, they are not same. Any of the poles are not repetitive. Instead of that, they are distinct, means p1, p2, pn are distinct pole. So that's why here the condition we have taken pi not equal to pj. So now here we will proceed that if we are able to express the transfer function in the form of 34, then the diagonal canonical form will be look like this, that is x dot will be equal to the A matrix. You can see in A matrix all the diagonal elements are the poles of the transfer function. You can see that minus p1 minus p2 minus pn, so only the diagonal elements are present, so that's why this form is known as diagonal canonical form, and all the other entries will be 0. So here this is 0 and here this is 0, and only the diagonal elements will be present in the A matrix, and the diagonal elements will be the pole of the system or pole of the characteristics equation. And the B matrix, here you can see all the elements are 1, and the C matrix, you can see in the C matrix C1 C2 Cn are the entries of C matrix, and you can see that where the C1 C2 and Cn are sitting in the partial fraction expansion. So now the question is how we will get this representation out of this transfer function. So now thing is that first our intention will be to draw the block diagram, and from the block diagram we will try to identify the state variables. So now as I told you that when you will write when you will draw the block diagram, then you have to start from input and you have to end with the output. So let us start to draw the block diagram of the output equation, that is y is equal to b0 us plus c1 s plus p1 into u of s plus cn by s plus pn into us. So now first term we have implemented, so we have started with the input u, then u is multiplied with b0 and added with what factor? Now 1 by s plus p1, then multiplied with the coefficient c1, then it is added. So like that, 1 by s plus pn is multiplied with the coefficient cn and it is added. All these terms are added to get the y, and now the output of these blocks 1 by s plus p1, 1 by s plus p2 and 1 by s plus p1 are identified as a state variable. So suppose this is x1 and this is x2 and this is xn. So now if these are identified as a state variables, next will be to write the state equation. So how we will write the state equation from the block diagram? The block diagram, you can see that the x1 dot. So now if we want to write the x1 of s, then what we can write? Now we can write from here the x1 of s is equal to 1 by s plus p1 into us, because for this block the input is us. So now we can write x1 of s is equal to 1 by s plus p1 into u of s. Similarly, other terms we can write x of ns is equal to 1 by s plus pn into us. So these are the n number of state equations we are getting, and now if we will cross multiply, then ultimately we will get the state equations in the Laplace domain in this, that is s into x plus 1. How we are getting? Now you have to just cross multiply, that is s plus p1 into, suppose first equation, that is x1 of s is equal to u of s. So from here we can write s into x1 of s is equal to minus p1 x1 of s plus u of s. So similarly we can write for all other cases, that is s into x2s is equal to minus p2 into x2s plus us. Okay, so now after getting this, we know that state variable representation is a time domain representation. So our work will be transform this set of state equation in time domain. So what will be the time domain representation? The time domain representation will be, that is x1 dot is equal to minus p1 into x1 plus u, x2 dot is equal to minus p2 into x2 plus u, like that xn dot is equal to minus pn xn plus u. So now what will be the, so these are representing the state equation. So these are state equation. Now we have to find out the output equation also. So output equation from where we will get? Now output equation is very easy to write, because you see y of s is b0 into us plus this 1 by s means us by s plus p1 is x of s. So basically y of s is equal to b0 into us plus c1 into x1 of s. The block diagram was also saying like that y of s is equal to b0 into u of s plus c1 into x1 of s plus c2 into x2 of s, like that, plus cn into xn of s. So we will write the output equation in frequency domain, that is equation 39. And if we take the inverse Laplace transform of equation 39, then in time domain the output equation will be stated in 40. So now our work to write the vector matrix notation of 38 and 40. So if we want to write the vector matrix notation, then it is very easy to write, and we will get the state space representation like this. Because you see, first equation x1 dot is equal to minus p1 into x1 plus u, then x2 dot is equal to minus p2 into x2 into u. So only you will find that the diagonal elements will be the poles of the system, or we can say that now in terms of a matrix we can say that p1, p2, pn are the eigenvalues of the a matrix, because here we can see that the poles of the transfer functions are the eigenvalues of the A matrix, and the B matrix, all the elements will be 1, and Y will be C into X plus B0 into U, where elements of the C matrix are C1, C2, Cn. Fine. Now as I told you that each form what we are discussing having importance, later on we will discuss about their advantages or their uses. One thing you can see from the diagonal canonical form, that once the system is represented in diagonal canonical form, you can clearly visualize what are the eigenvalues of the system and what are their sign, and from there actually we can conclude about the stability of the system which is represented in state space. So when we will discuss the stability in state space, then we will recall this diagonal canonical form, and you will find that this form is going to be much helpful to decide about the stability of the system. But a little bit variation of the diagonal canonical form we will get if we will assume that the state variables like this, not here, we can assume that c1 by s plus p1 is x1 of s, c2 by s plus p2 x2 of s, or we will make it different, that is cap, and then it is x of n cap of s. Okay, so basically what I want to mean that x1 hat of s is equal to now c1 by s plus p1 into u of s. So if we will assume the state variables like this, then we will get a diagonal canonical form little bit in a different way, but in that case you will find that the A matrix, structure of the A matrix is not going to change, only the B and C matrices are going to change. So let us discuss that variant also. So here you see we have assumed that the state variables are x1 of s is equal to c1 by s plus p1 into u of s, and like that xn hat is equal to cn by s plus pn into u of s. Fine. So now again from here by cross multiplying we have tried to return that s into x1 of s is equal to minus p1 x1 of s plus c1 into us. So previously this c1 appeared in the output equation, now this c1, c2, cn are appeared as an input coefficients. So now if we transform it with the inverse Laplace transform, if we'll do, then we will get the set of state equations are like this, and we will get the output equation like 44, and only now we will represent it in a vector matrix notation, and at that time you will find that the structure of the A matrix is still same. All the eigenvalues of A or the poles of the transfer functions are occupying the diagonal places of A matrix, and the B matrix, now instead of 1 1 1 you are getting C1 C2 Cn, but the C matrix having all the elements 1. But still this is a diagonal canonical form, because here the form of A matrix is very important, where we can see that all the eigenvalues of A matrix or system, or we can say that the poles of the transfer functions are located as a diagonal elements of A matrix. To understand it, we have taken a small example that suppose a third order system is described by a third order differential equation where y is the output, u is the input. It is a seesaw system. So the transfer function can be represented ys by us is by 6 by s cube plus 6 s square plus 11 s plus 6, which can be factorized, that is s plus 1 into s plus 2 into s plus 3. So here you can clearly visualize the poles of the systems are -1, -2 and -3, and if we want to represent this one in diagonal canonical form, first step will be to find out the partial fraction expansion of this expression. And if you do the partial fraction expansion, then the this will be 3 by s plus 1 plus -6 by s plus 2 plus 3 by s plus 2. Now you just multiply us to get the output expression, and we can choose now the state variables as x1 hat s is equal to 3 by s plus 1 into u of s, okay, then x2 hat and x3 hat accordingly. And now we will write the s into x1 hat s into x2 hat s into x3 hat s. So now we will take the inverse Laplace transform. We will get the state equation, 3-state equation like this, and the output equation is simple. There will be the addition of the states only. So x1 plus x2 plus x3 hat. So this is the output expression. Now it is time to represent it in vector matrix notation, and this will be the A matrix for this system, and this will be the B, and this will be the C. And most interestingly, that you can see the diagonal elements are the eigenvalues of A, which are the poles of the transfer function. So as I told you that this representation we will discuss when we will discuss about the stability of the system when it is represented in state space, and we will see that how this diagonal representation of a system is going to be helpful to determine the stability of a system. And also here I want to mention that you will find to find out the solution of a system, means for a given input, if you want to compute the output yt, then you have to solve the state equations. And that time also you will find that if the system is represented in diagonal canonical form, then it will be very easy in calculation to find out the system response. Now we will discuss about the Jordan canonical form. Here we will discuss the case if their roots are repetitive, then how we will get the form. So now here as an example we can see that the equation 50, where the P1 pole is repeated 3 times. So where the system involves a triple pole at s equal to minus P1, and all other poles, that is P4, P5, Pn are distinct. If we have this kind of transfer function, then how we will get the representation in state space, and that is actually the Jordan canonical form. Let us see how we will do. So the partial fraction expansion, again the same thing. Once you will get the transfer function in this form, next step will be to represent it using partial fraction expansion. The partial fraction expansion of this equation 50 will be b0 plus c1 s plus p1 cube plus c2 s plus p1 square, c3 s plus p1 plus c4 s plus p4, cn s plus pn. Okay, so now if we want to represent this input output relation in block diagram, how it will be. So now how we will implement this c1 by s plus p1 cube, c2 s plus p1 square, and c3 s plus p1, because this root p1 is repeated 3 times. So now how we will represent that this one now in this way, that is u input is there okay, then 1 by s plus p1, then again s plus 1 by s plus p1, 1 by s plus p1, then c1 into s plus p1, so c1 into s plus p1 whole cube, okay. You see c1 s plus p1 whole cube. So these three blocks will be multiplied. So ultimately here we are getting c1 by s plus p1 whole cube. Now we have to get another term c2 into s plus p1 whole square. So from here we have tapped the signal. So then we will get here, ultimately we will get c2 by s, here we will get c2 by s plus p1 whole square, and here ultimately c3 by s plus p1, and all other terms will be as usual, that is 1 by s plus 4 into c4 and 1 by s plus pn into cn. To get the output y, we will sum all this along with the b0 into u, we will sum all these terms, okay. Now we will define the state variables. So output of this blocks, one state variable we have assumed x1, and this state variable we have assumed x2, and this is as a x3, and all other x4, x5, xn. Fine. Now how the x1 and x2 are related. You see the x1 by x2, x1s by x2s, if you find out, that is by 1 by s plus p1, okay. And how the x2s by x3s are related, that is also 1 by s plus p1. And how the x3s is related, now x3s is related 1 by s plus p1 into us, okay. And here I think I have missed the coefficients. Yes, coefficients we have missed, that is once we are writing, that is x1 by x2, yes, it is fine. So x1 by x2, you see x1 by here, if you see, that is yes, x1 by x2 is 1 by s plus p1, and x2s by x3 1 by s plus p1, okay. So now mathematically how we will get, this is the block diagram representation we can see, but mathematically how we can get that one. So to get that one, what we can do, we can define the state variables in this way. x1 of s is equal to 1 by s plus p1 whole cube, because you see the x1 of s, what you have defined, it is basically 1 by s plus p1 whole cube, okay, into u of s. And then similarly x2s by is equal to 1 by s plus p1 square u of s, and x3s is equal to 1 by s plus p1 us, and all other terms will be simple because they do not have any multiplicity in the pole locations. So now to get rid of this cube square term, what we will do, we will find out x1 by x2, then we will find that we are finally going to get 1 by s plus p1, and similarly x2s by x3s we will get 1 by s plus p1. Now we will represent these equations in this way, that if you write this equation, x1 by x2s can be written in this way, and then x2s by x3s by 1 by s plus 1 can be written in this way, and all other terms means starting from x3, you see x3, x4, xn are in a normal way, and we are getting the equations like this, that is s into x3s is minus p1 into x3s plus us, like s into xns is equal to minus p and xns plus us. Now if we want to transform, if you take the inverse Laplace transform, then the state equations are like this. and the output equation ultimately will be expressed by y equal to c1 into x1 plus c2 into x2 plus cn into xn plus b0 into u. Now we have to represent this state equation in vector matrix notation. Mind that in these two terms no u terms are there. It is minus p1 into 1 into x2 and it is minus p2 into x2 plus 1 into x3. So how it look like? So if you represent it in a vector matrix notation, the notation will be like this. That first three state you see that x1 dot, x2 dot and x3 dot. If you see that one, then you can clearly divide this matrix in this way. Okay, so first you can see that minus p4 to minus pn, it is purely a diagonal matrix. This sub matrix, if you see, it is a purely diagonal because p4 to pn, all the poles or the eigenvalues are distinct, and the p1, sorry, here it will be not p2, it will be p1. So minus p1 minus p1 minus p1 is sitting in a diagonal, but this small matrix is not actually the pure diagonal matrix because the off diagonal terms are present 1 1 due to the expression of x1 dot, that is minus p1 x1 into 1 into x2, and x2 dot is equal to minus p1 into x2 plus 1 into x3. Okay, so this representation, and that's why the first two term of B matrix are 0, all other elements are 1, and the Y having C over C matrix having C1 C2 Cn. So this is the C matrix. Now this representation is known as Jordan canonical form, where you can see that it is not purely a diagonal representation because repetitive roots are there, and due to that the structure of the A matrix will be like this. So this is the Jordan canonical form, and we will try to understand using a small example where you can see the transfer function is taken where s plus 1 square, so the pole minus 1 are repeated 2 times. So how we can represent this in Jordan canonical form? So now we have to first step we have to find out the partial fraction expansion. So let us find out the partial fraction expansion, which will be expressed by 3 by s plus 1 whole square plus minus 1 by s plus 1 plus 3 by s plus 2, and the output equation can be written by multiplying us. Now we will assume the state variables, that is x1s is equal to 1 by s plus 1 whole square into us, x2s is equal to 1 by s plus 1 into us, and x3 hat is equal to 1 by s plus 2 into us. Now here, to avoid this square term, we will take the ratio of x1s by x2s, and which is written here, and other two expressions are as usual. And now if we transform inverse Laplace transform, we will get the state equation, and the output equation is expressed in 56, and ultimately we can see the Jordan canonical form, where you can identify the division of matrices like this. You see that minus 2, which is the distinct root, are sitting here, but this small matrix is not pure diagonal. A off diagonal term is present 1, and the two repetitive eigenvalues or the poles are located at the diagonal place, that is minus 1 and minus 1. So in this way we can represent the system in transfer function. If you see that multiple roots are there, then we will get the Jordan canonical form, and in this way we will find out the Jordan canonical form for a given transfer function. So this is the all about for today's discussion, and now I will conclude with the summarization that today we have learned two canonical representation, that is diagonal canonical form and Jordan canonical form, and all together we have learned some of the most important canonical representations. But the uses of these representations definitely we will discuss when the topic, a suitable topic will come, and then we will refer all these or we will take the reference of all these representations. Thank you.